Now, let's have a look at the area of a triangle, and specifically a formula that works quite well with non-right angle triangles, though it works with any triangle. Now, the formula for the area of a triangle that we have known for years is area is equal to half the base by the perpendicular height. So if we know a base and we knew the perpendicular height away from that base, if we knew the base and the perpendicular height away from that base, the distance, perpendicular distance from the base out to the furthest away point, the furthest vertex, or the opposite vertex, that would give us the area of a triangle. But if I draw in that situation as I've done in here, if I know this side, the base, and the angle in between, what we call the included angle, we're actually able to find the height in terms of A and C. Now, why do I say that? Because if I think about what I know about a right angle triangle, I've created a right angle triangle inside my non-right angle triangle by getting the perpendicular height. So this bit in here is a right angle triangle I have created inside of my non-right angle triangle. And I'm going to use that to rewrite the area formula in this form here. So I've got the sine of C would equal the opposite over the hypotenuse. The opposite over the hypotenuse would be h over a. Rearranging then, h would be equal to a sine c. Subbing that into the formula I have known for years, I get half ab sine c. That's just a quick derivation, and it's good to, I'm primarily showing it to you because it's good to highlight to you that you can create right angles by getting perpendicular distances from bases from time to time. Doesn't come up massively often, but being able to play around with a diagram like that has been important in different contexts in exams. Now, that's how you can derive that should you ever be asked to. The formula itself is on page 16 in your log tables, along with the sine rule, the cosine rule, and sine, cos, and tan, and Pythagoras. Now, let's put this into practice. If we know two sides of a triangle and the included angle, the angle in between, that's when we're able to use our formula. So this diagram, or an equivalent to this diagram, is on page 16 to remind you of what information you need in order to be able to sub into this formula. You must know two sides and the angle in between them in order to use this formula, or you must be able to find that information before you can sub into that formula. Now here, we've got a side of length 3 units, a side of length 6 units, and the angle in between is 40 degrees. What would be the area of that triangle? Well, I have the information I need. I have two sides and the included angle, the angle in between. So let's just sub into our formula. I go to my log tables and I write it down. And now I just sub in. It doesn't matter which you pick as A and B. If there is something that's obviously a sensible base, then it can make more intuitive sense to make that the base. So here, 6 would be the sensible base to write down, but it will work in any case. Half on 3 by 6 sine of 40 is my area. And I just throw all of that into the calculator. That's all numbers now. So when I put that into the calculator, I get 5.7851. And usually in the exam, I will be asked to give my answer to 1 or 2 decimal places. Here I'll say that I'm going to give it to 1 decimal place. Or actually, normally if they didn't ask, you'd go to 2. And as I didn't write it down, let's go to 2. So final answer then would be rounded to 2 decimal places. And I would know that because it's an area, I would write down units squared for my units of my answer. And squared because it's an area. Now, let's go on to a slightly more advanced example. The trick that can come in with using this formula is if you're asked to find that angle instead of being given it. And it's the same issue that has come up before with the sine rule and with the unit circle in general. We're effectively getting the height above our baseline here. Now there's two angles. If I had my angle of 40 degrees here, that gives me a particular height above the base. But if I had an angle of 140 going up this way, and I had the same two sides, 3 and 6, I'd get an equal area to that triangle because it would end up having the same perpendicular height. So let's look at that in practice here. If they've given us the area of 6 meters squared and sides AB of, so we have a triangle, 6 meters squared area, the side length AB is 8, the side length AC is 3. What is the angle CAB? Well, let's draw this in as we always should to start off our questions. So we would call this A, B, C. We have the area is 6 meters squared. AB is 8 meters. Yeah, they're in meters, my apologies. It's 8 meters. AC is 3 meters. And I want to know CAB. C to A to B. I want to know this angle here. I'm going to call it theta. So I want to know theta. Now the thing that I should have in my head is that because I'm using sine, I figure out I'm looking for the area. I'm going to write down my formula. So steps in my question are: draw your picture, write down your relevant formula. When I write down my relevant formula, I cop that I'm going to be looking for sine, and I know that there could be an acute and an obtuse version of this diagram. I could have drawn it out as so. Three, 8, A, B, C. I would have had 6 meters squared here, and I could have had my angle theta there. Both of those would have ended up with the same perpendicular height, so both of them would have had our area of 6 meters squared. So I need to find both versions of CAB. Often in an exam question, they might ask you for either the acute or the obtuse result, and in that case, you only need to give one or the other. But if they don't mention it, you have to give both possible solutions because they're both valid solutions. Both of these thetas, whatever they are, would give us the correct perpendicular height. Both of them would give the same area, so both of them need to be taken into account as possible solutions. Now, let's just sub into our formula naively, and we're going to have area. I've written down my formula here, so I'm subbing in. Area is equal to 1/2 on 3 on 8 on sine theta, and I'm looking for theta, so I end up with 6 is equal to 12 sine theta. Rearranging sine theta is going to be equal to 1/2. Then I see I have sine theta is equal to some positive fraction. Where could that happen? It could happen in the first quadrant, or it could happen in the second quadrant. So I'm dealing with a situation where I'm in either the first or the second quadrant. I'm going to get my reference angle, my alpha, Let me redraw that. I'm going to get my alpha, my reference angle, and then I'm going to find out my two possible solutions. So my sine of my reference angle would be opposite. Would be my opposite over my hypotenuse. This is just a ratio. There's no particular reason these angles. This is the ratio of a half. This is not to say that those numbers will actually be 1 and 2, just that the ratio simplifies to a half. Now, I have that. That's going to be my mean that I have sine of alpha is going to be a half. Get inverse sine of both sides, and we get the angle is going to be 30 degrees. So theta in the first quadrant, in quadrant 1, my angle theta is just going to be 30 degrees. That's in the first quadrant. And in the second quadrant, theta would be 180 minus 30 to get up to the same height, the same value of y. It's going to be 180 minus 30. It's 150 degrees. So the two possible angles that I could have been going up at would be 30 degrees or 150 degrees. Both would give the same perpendicular height, therefore both of them are valid ways of getting our area of 6 meters squared. So that is the only extra bit that can really come into our area formula for our triangle. And again, you need two sides and then the included angle, the angle in between, in order to be able to use this formula. And if we're asked for the angle, we have to be conscious that there is an acute and obtuse possibility, because our height could be up here in the first quadrant or up here in the second quadrant. And that's